Good day to everyone. Today, me and my groupmates are going to tackle about evaporation. So under evaporation, we have different contents such as introduction to evaporation, physics of evaporation, factors affecting evaporation, measurements of different factors for evaporation, and available methods or procedures for estimating evaporation from open water.
A pleasant day to all of you. To start the report, we have here the introduction to evaporation. So first, what is evaporation? Evaporation is the process in which a liquid changes to the gaseous state at the free surface below the boiling point through the transfer of heat energy. So, evaporation happens when a liquid turns into gas. As water is heated below the boiling point, it evaporates and becomes a gas. One example of this is when wet clothes dry in the sun. The water is not actually disappearing, rather, it is evaporating. So, next, it is also one of the three main steps in the global water cycle, namely evaporation, condensation, and precipitation. Water cycle is a phenomenon that happens globally. Evaporation being one in the main steps of water cycle, it is significant for the 90% of the moisture in the atmosphere of the earth and 10% for the transpiration of plants. And the water cycle demonstrates how water is constantly moving both inside the earth and in the atmosphere. It is a complicated system with a wide range of processes. Water vapor is created when liquid water evaporates, and this water vapor then condenses to form clouds and falls or precipitates back to earth as rain and snow. Evaporated gas is called water vapor. So when we say water vapor, it is the molecules of liquid water suspended in the air. In the water cycle, evaporation occurs when sunlight warms the surface of the water. The heat from the sun makes the water molecules move faster and faster until they move so fast they escape as a gas. As a liquid is heated, it evaporates. This indicates that the liquid's molecules must develop kinetic energy. As a liquid gains kinetic energy, its molecules spread out and vibrate more quickly. The outcome is a change in the liquid's state of matter, turning it into a gas. Substances can exist in three main states: solid, liquid, and gas. Evaporation is just one way a substance, like water, can change between these states. These changes between states, like melting, freezing, and evaporating, happen because as the temperature either increases or decreases, the molecules in a substance begin to speed up or slow down. These changes in state is mainly because of the temperature. So as the temperature of liquid water falls low enough, it freezes and solidifies into ice. If water is heated sufficiently, it will melt and change back into a liquid. Further heating causes the water to evaporate and turn into water vapor.
Physics of evaporation. Evaporation happens when the liquid turns into a gas. The process begins when the liquid gets energy in the form of heat. Adding heat to water causes molecules to become increasingly energized and they start moving more rapidly. This means that the liquid's molecules have to gain kinetic energy, resulting in increase in distance between the liquid molecules and weakening of the forces between them. As a liquid's molecule gain kinetic energy, the molecules begin to spread apart and vibrate faster, causing the liquid to change its matter from liquid to gas. At high temperature, more of the molecules near the water surface will tend to fly off into lower layers of the overlying air. At the same time, water vapor molecules in the lower air layers are also in continuous motion and some of them penetrate into underlying mass of water. Water is a common substance where evaporation will take place. When energy or heat is added to water, the bonds that hold the molecule together begin to break. The temperature at which water will turn from liquid to gas is its boiling point, 212 degrees Fahrenheit or 100 degrees Celsius. The rate of evaporation depends on vapor pressure, temperature, wind speed, atmospheric pressure, soluble salts, heat storage, and water bodies. Vapor pressure. The rate of evaporation is proportional to the difference between the saturation vapor pressure at the water temperature and the actual vapor pressure in the air. This equation is called Dalton's law of evaporation. Evaporation occurs till the water temperature is equal to the vapor pressure in the air. Next is the temperature. The rate of evaporation increases with an increase in water temperature. Although there is an increase in the rate of evaporation with increase in air temperature, a high correlation does not exist in between. Wind. Wind helps to remove the evaporated water vapor from the zone of evaporation, thereby creating greater scope of evaporation. The rate of evaporation increases with increase in wind velocity up to some limit or critical wind speed, and thereafter any further increase in wind velocity does not have any effect on the evaporation rates. This critical wind speed value is a function of the size of the water surface, large water bodies to high wind speeds. Atmospheric pressure. Other factors remaining the same, a decrease in atmospheric pressure or as in high altitude areas increases the evaporation rate. Soluble salts. When a solute is dissolved in water, the vapor pressure of the solution is less than that of pure water and hence it causes reduction in the rate of evaporation. The percentage reduction in the evaporation rate approximately corresponds to the percentage increase in the specific gravity under identical conditions. Evaporation from seawater is about 2 to 3% less than that from fresh water. Heat storage in water bodies. Deep water bodies have more heat storage capacity than shallow water bodies. The effect of heat storage is to change the seasonal evaporation rates and the annual evaporation remains more or less unaltered.
So let's proceed to the factors affecting evaporation. First is the temperature. The greater the temperature of the liquid and its surroundings, the faster the rate of evaporation. When the temperature of the liquid, water in this case, is increased, it results in an increase in the kinetic energy of the individual molecules that constitute the liquid. This increase in energy makes it easier for the liquid molecules to overcome the intermolecular forces of attraction that holds the liquid together and escape into the atmosphere as a gas. The next factor is the surface area occupied by the liquid. Since evaporation is a surface phenomenon, the greater the surface area occupied by the liquid, the quicker it undergoes evaporation. So liquids are known not to have any definite shape. They assume the shape of their container. Therefore, the greater the surface area of the container, or the greater the surface occupied by the liquid, the greater the number of liquid molecules present at the surface. The larger the number of liquid molecules at the surface, the larger the number of molecules that will break away from the liquid and becomes a gas at a given point of time, which contributes to the increase in the rate of evaporation. The third factor is the humidity of the surroundings. The greater the humidity of the atmosphere surrounding the water, the slower the rate of evaporation. There is a limit to how much water vapor the atmosphere can hold. This limit is proportional to the temperature, which implies that hot air can hold more water vapor than the cold air. An increase in temperature with constant humidity will contribute to an increase in the rate of evaporation since hot air can hold a greater amount of water vapor. The last factor is the air circulation or wind speed. The presence of breeze and another source of air circulation directly contributes towards the rate of evaporation. The presence of a breeze, a powerful wind, and some other form of air circulation can speed up this process and make the environment of the liquid less humid. Therefore, by decreasing the humidity of the liquid surrounding, a powerful breeze or wind can increase the rate of which the liquid evaporates.
Measurements of different factors for evaporation. Estimation of evaporation is of utmost importance in many hydrologic problems associated with planning and operation of reservoirs and irrigation systems. In arid zones, this estimation is particularly important to conserve the scarce water resources. However, the exact measurement of evaporation from a large body of water is indeed one of the most difficult tasks. So, ang measurements of different factors for evaporation po is important kasi para malaman po natin kung magkakaroon or may shortage po ba ng water resources sa isang lugar. And also po, habang tumatagal is mas lalong dumadami or mas tumataas po ang demand ng tubig sa isang lugar. So, ito po na measurements of different factors for evaporation is kailangan para makagawa na po ng paraan para maiwasan na po ang shortage sa isang lugar. Measurement of evaporation. Evaporation is usually measured by evaporated pans and atmometers. Evaporation pans are most widely used for measuring evaporation. It is affected by the size, depth, and location of the pan. So, ang evaporation po, pwede po siyang ma-measure by two types, evaporated pans and atmometers. Although, we only focused on evaporated pans. Type of evaporation pans. The first type is Class A evaporation pan. It is a standard pan of 1,210 mm diameter and 255 mm depth used by the U.S. Weather Bureau. The depth of the water is maintained between 18 centimeters and 20 centimeters. The pan is normally made of unpainted galvanized iron sheet. So, ang pan po is parang i-represent niya ang open body of water. So, it is filled with water and exposed on a flat plateau. Evaporation rate is calculated by the change in level of the free water. So, chine-check po nitong evaporation pan kung gaano kabilis or gaano kadami yung na-evaporate in a specific amount of time. Colorado Sunken Pan. This pan is 920 mm square and 460 mm deep, is made up of unpainted galvanized iron sheet and buried into the ground within 100 millimeters of the top. The primary advantage of this pan is its aerodynamic and radiation characteristics are similar to that of a lake. The drawback of Colorado Sunken Pan is difficult to detect leaks, is expensive to install. Extra care is needed to keep the surrounding area free from tall grass, dust, and etc. So, ang advantage po nito na pan is kaya po siya tinatawag na similar sa lake kasi po buried siya 10 centimeters of the top. So, enclosed po siya. So, parang di po magmamatter kung ano po yung mga nasa side ng pan. Magmamatter lang po yung aerodynamic since siya lang po yung pwedeng makagalaw or mag-affect sa water since pwede po siya dumaan sa may or pwede po siya maka-affect sa top part ng pan. Ang drawback po ng Colorado Sunken Pan is difficult to detect leaks since buried po siya 10 centimeters of the top. So, di po makikita sa ilalim kung nagkakaroon na po ba ng leaks ang pan? US Geological Survey floating pan with a view to stimulate the characteristics of a large body of water. This square pan with a dimension of 900 mm sides and 450 mm depth is supported by drum of floats in the middle of a raft with 4.25 mm by 4.87 base set afloat in a lake. So, ang US Geological Survey floating pan is similar lang po sa Colorado Sunken Pan, sadyang ang Colorado Sunken Pan is buried into the ground, pero ang Geological Survey floating pan is floating in a large body of water. Pan coefficient. Evaporation pans are not exact models of large reservoirs and have the following principal drawbacks. Number one is they differ in the heat storing capacity and heat transfer from the sides and bottom. Number two, the height of the rim in an evaporation pan affects the wind action over the surface. And number three, heat transfer characteristics of the pan material is different from that of the reservoir. So, all in all po, nagmamatter po ang placing ng evaporation pan sa heat storage and heat transfer. And also po, nagmamatter kung ano po ang material na ginamit sa paggawa ng pan sa heat transfer. Here is an example of measurement of evaporation. If a lake has a 500-hectare surface area, compute the daily lake evaporation for the data given. Assume the pan coefficient is 0.8. Compute the 6-day evaporation and loss of water in kilograms or tons. So, day 1 has 1.5 pan evaporation in centimeters. In day 2 is 2.2. 3 is 0.6. Day 4 is 1.2. Day 5 is 0.7. And day 6 is 1.7. So, for the solution po, para makuha po ang lake evaporation niya, is i-multiply lang po natin ang given na daily pan evaporation in centimeters sa pan coefficient na in-assume po natin na 0.8. So, for day 1 is 1.5 times 0.8 is equals to 1.2. Day 2 is 2.2 times 0.8 is equals to 1.76 and so on. So, ang 6-day evaporation po is ang total natin which is 6.32. Ang total po ng 1.2, 1.76, 0.48, 0.96, 0.56, and 1.36. So, 6-day loss of water which is equals to 6.32 divided by 100 para po maging meters ang unit niya times 500 kasi po yun ang hectares and times 10,000 meters squared is para po magkaroon po ng sa metric tons which has a total of 316,000 cubic meter or 316 times 10 raised to 3 metric tons.
Good day, viewers. Here are some available methods or procedures in estimating evaporation on open waters. Let us proceed with the first method, which is the water budget method. The water budget method is the most straightforward and least accurate of the analytical techniques. It entails formulating the lake's hydrological continuity equation and calculating evaporation based on the information or estimation of other factors. Herewith is the formula used for the method, which is this first equation. The second equation is the simplest form of the formula because it mainly targets to find the daily lake evaporation or that variable which is marked as EL. If you don't understand it, here are also stated the meaning of the variables in the formula. Please keep in mind that all quantities in this method are in units of volume or cubic meters or in the depth in millimeters over a reference area. In these terms, the daily precipitation, the daily surface inflow and outflow of the lake can be measured together with the increase in lake storage in a day. However, it is not possible to measure the daily ground flow groundwater inflow, the daily seepage outflow, and the daily transpiration loss, and therefore these quantities can only be estimated. Transpiration losses can be considered to be insignificant in some reservoir if the unit of time is kept large, say weeks or months. Better accuracy in the estimate of the daily lake evaporation is possible. In view of the various uncertainties in the estimated values and possibilities of errors in measured variables, the water budget method cannot be expected to give very accurate results. However, again, controlled studies such as the Lake Finer in USA 1952 have given fairly accurate results by this method. The second method here is the energy budget method. So, the principle of energy conservation is being used here. The energy available for evaporation is calculated by taking into account the energy entering, leaving, and being stored in the water body over a predetermined period of time. As we can see here in the slide, there is a figure representing all of the factors needed for the energy budget method. So we can see here the flow or the actions going on, such as the heat flux, the solar radiation, the back radiation, and other factors. So with these factors, here is the stated formula for the energy budget method. And here are the valuing variables that will define each variable in the formula. So, we have here the heat energy received by the water surface, and we also have the sensible heat transfer, the heat energy used up in evaporation, the heat flux into the ground, the heat stored in water body, and the net heat conducted out of the system by the water flow. So as we can see here that there are also some variables that are required to be calculated, not just to be seen or to be estimated in a figure or somehow in a simple situation, in a problem such as these kinds of figures. All the energy items or the energy terms here are in calories per square millimeter per day. If the time periods are short, the terms heat stored in water body and the net heat conducted out of the system by water flow can be neglected as negligibly small. All the terms except the HA or somehow the sensible heat transfer from water surface to air can either be measured or evaluated indirectly. The sensible heat term transfer, which cannot be readily measured, is estimated using Bowen's ratio with the given expression. Stating here all of its legends as well. And together with that, we can also have a new method on how the EL can be evaluated. So as we can see here, the estimation of evaporation in a lake by the energy balance method has been found to give satisfactory results, with errors of the order of 5% when applied to periods less than a week. Further details of the energy budget method are available in some references, but in this situation, I think you understand how the formula should go. Next is we have the mass transfer method. So as we can see here, there is no stated formula due to different formulas stated by different references. So I am just going to give here some description with this method. So the mass water vapor transfer from the surface to the surrounding atmosphere is calculated using this method, which is based on theories of turbulent mass transfer in the boundary layer. This method can produce accurate findings when using numbers measured to high-end, more expensive instrumentation. Herewith, with the last slide, we also have two more additional methods in estimating evaporation in open waters. So we have the mass balance method and the pan evaporation method, which is only a summarized description together with their summarized formula. So in the method, the mass balance method, it is simple in principle and evaporation is calculated as the change in volume of water stored and the difference between inflow and outflow. Some reference has said that it has a similar process or technique with the water budget method. So herewith is the formula for the mass balance. And last we have the pan evaporation method in which it has an intuitive appeal of calculation in a visible way. It is achieved by taking a ratio of the bulk mass transfer equations of lake and the pan. So it is also stated here with some of the formula. So with all of those discussions about evaporation, together with the methods and other physics behavior measurements, this ends the discussion. So we hope that you have learned something in terms with evaporation useful for the subject hydrology. That's all and have a good day.